Can you give me the link for the show?
The YouTube link to the show? Sure.
Yeah.
Large blows. And I guess I'll close it down. Okay. So what's happening in Houston? Some Lunar Planetary Society thing?
Yeah. So I managed to accidentally sleep through the series results this morning. Don't ever take your heavy-duty allergy meds before going to bed is the lesson I learned. But there's all Pluto all the time this afternoon, as well as more series stuff. So I'm going to go try and catch that. So I appreciate recording early.
Do you know what the white spots are yet?
It's salts.
But they're blinking.
That's all right. It can be salts that are embedded in volatiles that melt and rephrase.
All right. I got a book just about 10 minutes before noon. So, and I know you're, okay. I'm sure.
Yeah, I'm happy with just recording and then.
Yeah, we'll do the show. Maybe a couple of questions. Anyway, we're catching everybody off guard anyway. Yeah. We're doing this an hour early, so it's really.
F407.
Yes, 407.
Okay. So, welcome to Chaos, everybody.
Yeah, and Pamela's not in her normal location.
Nope, and I don't know how to spell cannibalism.
Cannibalism.
Aha.
And nib.
See, the problem was I was also mispronouncing it. So that first I had completely wrong. Sounding things out only works if you pronounce things correctly. And we all know I don't pronounce anything correctly.
No. Hey, everybody, say hi, and then I can say hi back to you. So we've been having some weirdness with Hangouts, with live streaming, with the YouTube integration, with the Hangouts on air. So
this will be an adventure.
Well, yeah. I mean, and also, I'm about to throw gut-wrenching change at everybody. So I think in the next probably month or so, we will start playing around with other methods of streaming. I know you tried to muck around with it a bit, but anyway, I love now when I sort of let people know that change is going to happen. You're like, it's Fraser. It's what happens. So, yeah, I'm going to look for some good kind of integrated streaming, essentially a production system that I can run off this computer and then stream that out through YouTube. And that way we're not dependent on the integration with the Hangouts, which we're using right now, which is wonderful because it's so easy to use. But, you can't use all the good features in YouTube when you're streaming from multiple computers. And the second they decide they don't want to use it anymore, we're toast. So, I don't like to be toast. It's the problem with Google. As soon as we fall in love with something and adopt it, they get rid of it. Yeah, exactly. Google Reader, anyone? Okay, I'm going to say hi to a bunch of people who are here and are aware. Now, if you haven't, you should make sure that you subscribe to Astronomy Cast on YouTube. Another Google thing. We love you, Google. But then also go in and muck with your settings and set your notifications and go ahead and make sure that you get notified when we go live. And that way you're like hanging out and you're like having your coffee and you're like, what? Astronomy Cast, something's happening right now? Because we sometimes change when we record because we're a podcast that just happens to record live in front of a not quite studio audience. And we don't control when interesting news about Pluto gets announced. Or things like last week when I got hit by a nasty Adobe software bug that ate my computer. Oh, no. Did it eat your computer? Oh. It ate my config directory, so I had to do a reinstall of a bunch of software. But I'm going to say hi.
Okay.
Oh, sorry. Christian Berndt, David Fairweather, Ilid Avron, Fadumo Ishmael, Guido Bibra, Helga Bjerkog, Joe Rushton, John Gallant, Michael Thompson, Nancy Graziano, Ryan Marquise, Sylvan Westby, Stephanie Martinez, and Tom Van Scotter. Hey, everybody. Welcome to Astronomy Cast. A couple of new names here, which was cool, even though we're doing this at a funny time. Yeah, Jason Rambles, you just made it in. Johnny Zed. I hope you're Canadian or British when I say Johnny Zed, and then you're like, yeah, that's the way you pronounce it. Yeah, so I've been playing around. I got a Steam link just a couple of days ago, which has been super fun. Yeah, and so I've been streaming from this computer to my television and playing games with a Steam controller. It's pretty fun. Pretty fragile. So, crashes a lot, but you can see the future there, which is like you have one computer and you just stream it to all the different TVs in the house and you play games. There's no lag. It's really neat.
Cool.
Yeah. So how long are you in Houston for?
I am here until early in the morning on Friday, and then I'm taking an early flight out. And so I'm here to try and catch up as much as I can on planetary science, meet people. We're trying to recruit people for a few different jobs. So if you are a data scientist or a Earth and planetary scientist or an astronomy helio person, we have 3 different postdoctoral fellowship positions that are either open or getting ready to open at SIUE and at the Planetary Science Institute. So I'm here just getting the good word out.
So if I understand correctly, you are not begging for money. You are now begging to spend money.
Yes. Yes, I am.
What a crazy world we live in. It's all topsy-turvy. All right, well, I think we should do a show.
Okay. I'm going to record on my handy-dandy little...
Zoom.
Yes. H4n, because I'm using...
All hail the H4n.
Okay.
By the way, for if people are wondering, that is the audio device that I do all the audio for the YouTube videos that I do. So I just plug in a lav mic into that thing, record the audio separately from the camera, and it's wonderful. If you want to just like not have any audio problems, get that thing. Hold it up again. There you go. Hold on. Now you're talking. Hold on. I'm talking. Wait. Okay. So you see here on the top here, it's got the 2 little microphones. They're not great. But what it does have is it's got 2 XLR inputs. Go to the bottom of it there. Yeah. So you see those 2 XLR inputs there, and you can use it as an audio device for your computer, which I don't know if that's what Pamela's doing, but you can take the thing. Yeah. So you can plug it in like a USB device into your computer, and then it's your microphone on your computer, and it's acceptable audio with the mics on it. But if you hook up like a lab, it's great, and it's like a Swiss Army knife for us.
The only thing is, if you're going through TSA, I actually checked my luggage strictly because I'm carrying this thing, because it looks like a taser. And if I get the wrong TSA person, my life is just ruined for a little while.
Well, I used to carry my my blue snowball, which looks like a bomb. So I would always get someone wondering, like, what is that thing? Except a couple of times, you're like, oh yeah, that's a microphone. I've seen those. Yeah.
So I check it in my baggage now, and that did cost me an hour of sleep last night because it took a while to get my bag, but.
Well, but then you can record some like off the top of your head podcasts. You can do some stream of consciousness stuff, some interview stuff. It's like I said, Swiss Army knife. If you want to get into audio production, want to record videos, anything, and you hate the way the audio sounds on your podcast, on your, if you're doing videos, YouTube videos, anything, and the audio sucks, it's because you don't have one of those. So, man, they don't even pay us money. We just gave them a huge shout out.
But we should record an episode because I want to go learn about Pluto.
All right.
Or learn more about Pluto.
Will you tell us next week what you found, or tell us on Friday what you found?
Yeah, and I will be tweeting as I go. So follow @StarStrider spelled with a Y. And hopefully there will be some good science. And I'll also be putting stuff out on Cosmic Quest X on Twitter.
That sounds awesome. All right, here we go.
Oh, I should press record on the correct device.
I have pressed record on the correct device.
I have now pressed record, and it shows pause, so I have to press that. I press that.
Yep.
Why aren't you recording? There we go. Now it's
Yeah.
recording. Hi, Preston. Sorry, I'm using a different device. I
How
hope
do your
this all
levels look?
sounds great. They look fine.
Yeah. Okay. Good. All right.
Okay, we're good. Maybe.
Yeah. The first time you press it, it sort of shows you how your levels are, and
Yeah.
then you can check it. And then the second time, it actually starts to record and get to know
I have
where
it
the whole
somewhat.
button is.
Yeah, it's also only pseudo-stable because I have it plugged into the wall socket, so I have it like precariously balanced at the moment.
Yeah.
Okay, we should still record.
Okay, here we go. Astronomy Cast, episode 407, Galactic Cannibalism. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser, Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good, and where are you doing?
I am in the Woodlands, which is a posh suburb on the north side of Houston, where they hold the Lunar and Planetary Sciences Conference every year. So I'm down here to try and absorb all I can about planetary science, even though I'm really a stars and galaxies kind of girl.
It feels like we just had you there yesterday.
I was at AGU, which is a similar group of people in December, and this is a once-a-year meeting, and this year it's all Ceres and all Pluto. I'm going to sneak in some Mars water as well, I think.
That sounds great. And so maybe next week you can give us a quick update on some of the really cool, interesting discoveries that were announced there.
That sounds like a plan.
Okay, right at the source. Okay, great. So last week we talked about stars feasting on other stars. This week we scale the whole process up a notch with galaxies feasting on other galaxies. Come for the carnage, stay for the science. All right, Pamela. So now, is cannibalism really the right term? Because someone mentioned in the comments before we started the show that really it's, they're kind of borrowing, they're merging, but there's absolutely carnage going on. So so what is the situation that leads us to this kind of galactic destruction?
So we actually do scientifically use the phrase galactic cannibalism. This area of astronomy actually has a lot of really violent terms. There's galaxy harassment, there's ram pressure stripping.
Bombardment, walk it off. Yep.
But galactic cannibalism is the process of one galaxy just systematically chowing down on another one.
And so what is the situation that's going to make this happen?
So normally it's something like, and we're doing this all the time with our Milky Way galaxy, there's a smaller galaxy flying along, and it happens to have a trajectory that intersects with our own galaxy or the galaxy that's going to eat it. And gravitationally, it gets pulled in, torn apart, and its constituent matter, its stars, its gas, all that sort of stuff, ends up getting consumed and made part of that parent galaxy, that massive eating cannibalistic galaxy.
And so, I guess when I always sort of imagine this, right, like, from the formation of the universe, all of the original galaxies formed, and then they've been in various parts gravitationally attracted to each other, and they just do these dances as they sort of come through and then merge over time as they sort of interact again and again. So did this happen to the Milky Way in the past?
So it's an ongoing process, and when we look at galaxies, we're looking at systems that formed in one of two different ways. A lot of the most massive elderly elliptical galaxies formed early on in our universe. They formed with the massive collapse of giant halos of dark matter and real matter, well, not real matter, dark matter and visible matter. Then you have everything else, which formed in more of all these little things that formed and then attracted to one another and formed something bigger and formed something bigger and formed something bigger. So nowadays, when we look out around our universe, we have these giant elliptical galaxies, which are commonly eating just about anything else. Then we have smaller galaxies that are still large, like our own Milky Way and the Andromeda galaxy that is nearby. And we're eating dwarf galaxies, little galaxies that are tens of thousands to a few million stars but are still much, much tinier. And when we eat these things, it is a fairly hidden process until you start looking at the ingredient list on the stars that have been eaten. So we can actually look around our Milky Way galaxy and find systems of stars that in some cases are orbiting in the wrong direction and are made up of slightly different material than everything else. And we're like, oh, that stuff was eaten from another galaxy.
Right. We see the tails or the trails of destroyed galaxies as this sort of smear in the night sky. We just go like that star, that star, that star. They're all related. And so they must have come from one gigantic or from one destruction event. But the galaxy itself, the dwarf galaxy, is long gone. It's now part of us.
And what's cool is since the Cylindrical Sky Survey launched several years ago, there has been year after year after year different tidal streams around our galaxy identified. And these tidal streams are often dwarf galaxies that in the process of getting gravitationally shredded by the Milky Way, left behind a smudge of stars that are all made of the same stuff and are, well, basically that smear of food that the galaxy is still sucking in.
And those are just the ones that have been recently consumed. We actually see a cloud of these smaller dwarf galaxies that were in the process either of sort of whipping around us or about to consume, right?
And it's not just these smears of stars, it's not just the dwarfs. We can actually see remnants of slightly bigger things that were eaten in our past. If we go outside and we very carefully look at all of the globular clusters, we see that some of them are orbiting in one direction around our galaxy, some of them are orbiting in the opposite direction around our galaxy. And the compositions of the ones that are going in one way are one composition, and the compositions of those that are going the other direction are a different composition. And it appears that a bunch of our Milky Way's globular clusters actually originated with a different, moderately sized galaxy that we chowed down on.
Now, those are the sort of the smaller ones, but I mean, there are some much larger collisions in our future.
Yes, and we see examples of this all around our universe. The mice is one of the more picturesque examples if you look at it in the Hubble catalog. And there's an entire catalog of our peculiar galaxies, many of which are galaxies in the process of merging together. And when you start to get galaxies that have a ratio of about 1 to 3, where one of the objects is 3 times bigger than the other object, or closer to the same size, so that you have a 1-to-1 ratio. So between 1 to 1 and 1 to 3, you end up with these massive dynamical events during these collisions where things end up looking like tadpoles, big spirally smudges of twisty arms, and there really aren't quite enough descriptive words to describe what is going on. But the result of all of this is you can take a couple of like perfectly innocent spiral galaxies and in the end have something that is more elliptical in shape, has lost all of this structure, is much more massive, and often for a while has a very active galactic nuclei in the center of this mess.
And so, you know, we look out and we see these, these galaxies out there. But, you know, when we look at the Milky Way, it still really has that fairly, nicely preserved disk, even distribution, doesn't seem to have that activity. So chances are the Milky Way hasn't had one of those collisions yet in the past.
No, that's coming in our future when we collide with the Andromeda and we become what some people call the Milkdromeda galaxy.
Yeah, that is the correct name, Milkdromeda, just so everyone is clear.
But there's a lot of side effects of these smaller collisions. You end up with things like the disk of a spiral galaxy like our Milky Way will get puffed out. So you end up with a thicker, what's called thick disk of the galaxy. And that's just inserting energy into the disk. You're smearing out all of the different orbits. You end up, in some cases, we look out and we see galaxies that actually have warps in the disk. So what should be a nice flat plate instead looks like it's slightly melted and it has been twisted into something that you wouldn't want to put food on. Galaxies get deformed in all sorts of more subtle ways in the smaller collisions. And this kind of makes sense. Smaller things can only have some impact on a system, but they are going to still be bringing in new matter. They're still going to be bringing in energy, and all of this is going to have an effect. So when our galaxy eats these little tiny dwarfs, we end up with a smear of stars, a few stars that have a completely different chemistry, and a slightly thickened disk to our galaxy. As you add more and more energy, eating something bigger and bigger and bigger, it deforms your shape more and more. And as you start to get to that 1:3 to 1:1 ratio, you have complete mutual assured destruction.
Right. And we're less massive than Andromeda.
Yes.
So we're the dwarf galaxy falling into Andromeda, although I think we're closer to that, as you said, that 1:1, that
the mutual assured destruction.
So sort of cast forward for us on how the next few billion years are going to play out.
Well, things are really going to start to get interesting in 4 to 5 billion years. This is going to be when our dark halos start to collide, when we start to see different ram pressure effects. Slowly, our systems are going to get these long tails behind them. 5.5 billion years from now, we won't quite be passing through each other. Conservation of angular momentum, it's going to be more of a whipping around one another. As we start to merge and collide, our two supermassive black holes are going to have to merge, or one of them will get flung away, but most likely they will eventually merge. And what's cool is, in general, stars won't collide, but with all of this gas and dust colliding, there's going to be massive amounts of star formation. So we're going to have these long tails of existing stars. We're going to have massive star formation down in the center of this mess. And in the end, we're going to end up with something that has very little gas and dust, because it's either going to get stripped out or it's going to get tangled up in star formation. And so we're going to have a slowly reddening system with almost no star formation once it's all over. So we're going to go from 2 alive, active, star-forming spiral galaxies to a massive burst of star formation during the collision and combining process to a dead elliptical.
So for a while there will look like the tadpole galaxies.
Yes.
Or perhaps some of those ones with, where you see and then you'll see the ones where they're sort of, well, I guess the tadpoles are, but they're sort of away from each other, but there's tidal tails connecting them together.
Yep.
And then what is an example of what the combined Milky Way and Andromeda will look like? I mean, we can see them in our telescopes now, right?
Just a generic elliptical galaxy. We're just going to be a cigar-shaped blob of stars.
Right. Like almost like these, I mean, these giant ellipticals, they almost look like a sphere, like a globular cluster.
So we do have to be
scale.
We do have to be careful, because there are giant elliptical galaxies, which are typically down in the centers of clusters. These are sometimes called CD galaxies, and these are truly massive systems that have grown out of the collision of many, many different objects. And then you have your generic run-of-the-mill, a few times the size of the Milky Way elliptical galaxies that, yeah, it's bigger than our Milky Way because it took like the Milky Way and the Andromeda to form it, but they aren't as giant, and they actually have lots of cool structures that are cigar-shaped, are spherical, and everything in between cigar and spherical.
But the thing that I find kind of really interesting is that it's like, until a galaxy has had one of those catastrophic events, it has that nice spiral structure. But it's that when 2 of those come together, they're, then it's a mess, because up until that point, it's like two solar systems colliding with each other, right? And that's when you get the mess. You get all the planets going at strange orbits, and things getting smashed into other things, and things getting shot out. So it's like when you look out and you do see those elliptical galaxies, that's when you know that they ended with that final catastrophic collision.
And it all comes down to energy. If you think about it, you throw up a thing of pizza dough, which is round, and you spin it, and it flattens out. So something like our Milky Way, just because of the nature of how it formed, you end up with this flattened, nice disk. Now, if you collide two disks at weird angles, you're no longer going to have a nice plate disk. So energy and angular momentum dictate the universe.
And I think one of the things that's really interesting is that by observing these galactic collisions, this was one of the ways that astronomers discovered dark matter, or were able to confirm the presence of dark matter as most likely a particle, right?
Right. And so when we look at some of the big collisions that are going on that aren't just between individual galaxies, but are between clusters of galaxies, you have a lot of the same physics, except now instead of dealing with particles that are stars and dust grains, you're now dealing with entire galaxies in the collision. So you have many more stars. The dust is a much different distribution. And when we look at the collisions of these systems, we can see when the gas, dust, stars, when that luminous material starts to interact, when it starts to shape out new forms. But with gravitational lensing, we're also able to see how the invisible dark matter changes the travel of the light coming behind that cluster, how it lenses that light, and we can trace out where the dark matter is, and we see the dark matter is just passing through one another quite happily, whereas the luminous matter is colliding quite violently. And it's in seeing that it's a mostly collisionless particle that we've started to get a better and better handle on what dark matter should be.
Right. Yeah. So yeah, you mentioned briefly about there's a few facets that I find really fascinating. I'd like to talk a bit about the star formation, because we do see some really interesting galaxies out there that have gone through this process of, some kind of galactic cannibalism going on there, and that creates these great eras of star formation.
So we see two different situations that lead to star formation getting triggered. First of all, you have two galaxies colliding, harassing one another, basically gravitationally interfering with one another, so that otherwise stable clouds of dust and gas are triggered to collapse. And what ends up happening is you go from having a nice, stable cloud of dust and gas that's thermally stable, it's supporting itself with its heat and gravity nicely balanced. And if you knock that out of balance, gravity takes over. And once gravity takes over, you end up with massive amounts of star formation. Now, this happens with galaxies colliding, but what's also cool is this happens when galaxies fall into clusters of galaxies. So you end up with clusters of galaxies on the outskirts will have lots of systems that are undergoing triggered star formation, where as the galaxy falls in, it hits the material that has already been stripped out of the galaxies in the cluster, and that, again, triggers star formation. So all sorts of different things can trigger star formation when interactions happen, but this also means that interactions lead to death. So when that galaxy falls into a cluster, it goes through massive star formation and then is dead. When two galaxies collide, they use up their gas and dust or stream it out behind them, and then they are dead. So galaxies live longer when left alone.
Right. But then they're a lot quieter, a lot sadder. I mean, we only have, what is it, like a couple of stars a year forming here in the Milky Way, while one of these starburst galaxies could have hundreds of stars forming a year. So it's just a whole, it's orders of magnitude. And it would be a crazy time to be in one of those galaxies while this is happening. The other part, I guess, has to do with those supermassive black holes. And you mentioned sort of, they might merge, one might get kicked out. What are the sort of physics involved with that?
Well, here it's all going to depend exactly on how the two black holes approach one another. Again, energy is king. And no matter what the final result is, you're also going to have a lot of the gas and dust that doesn't necessarily go straight into star formation. It's going to no longer have a nice stable orbit around the center of the original galaxy. It's going to be trying to figure out how to interact with this new center of mass. And a lot of that gas and dust is going to end up spiraling in towards the new center of mass of this new merging system. And as it spirals in, it forms an accretion disk. And this is where we end up with active galactic nuclei, which is kind of that catch-all phrase that we use for super bright QSOs, quasi-stellar objects, quasars. And we also use for the less bright ones that we see in our modern universe. So basically, anytime you end up with a disk of material falling in toward the black holes in the center of these systems, you get a whole lot of interesting physics going on. That disk itself can be quite bright. It can form radio jets coming off of it, massive magnetic fields. Again, death and destruction.
And I guess one of the things that's quite cool right now is, we are now post gravitational waves being detected directly by LIGO. And these are the kinds of events that LIGO, or, that would generate some of the most gravitational waves, right? It's these moments where these gigantic black holes are either smashing into each other or whipping around each other. That really bends your space-time.
And we're still trying to figure out how all of this happens, because one of the great mysteries is we look out at all of these merging systems and we don't find clear evidence of binary supermassive black holes quite as we'd expect to. So there's still a lot of work to be done. And a lot of it could be that we just don't have the resolutions yet to fully say this system only has one or this system has two black holes.
So let's kind of go forward into the future for sort of longer periods of time. Like, we see the Milky Way, it's going to consume a bunch of its dwarf galaxies around it. It's going to merge with Andromeda and sort of wrap that up maybe 7 to 10 billion years from now. But as we sort of continue the clock forward at billions, trillions of years, what's going to happen?
So we're slowly falling into a neighboring supercluster. And what's neat as all of this happens is it's a slow, gradual merger towards basically becoming a giant elliptical galaxy. But not everything necessarily will end up destroyed in the center. So we can't know precisely, are we going to end up in the center of a supercluster getting sucked in, or the white dwarf that is all that's left of our solar system getting sucked into this giant central galaxy? Or are we going to be lucky enough to be on an outer orbit where we get to sit back and watch the destruction of the universe?
Right. But eventually, I guess, everything that is gravitationally connected will either come together or enter some kind of stasis, I guess, if there's nothing else able to sort of perturb our orbit and move us closer to this galactic cluster. We'll end up just orbiting it forever. And then everything else will just be drifting away, or even accelerating away thanks to dark energy. So this whole, this time, when you think about it, we don't necessarily live in a special place in the universe, but we definitely live in a special time in the universe. And that there will be a time when this concept of galactic cannibalism goes away.
And it's not so much that it goes away as the period between collisions gets longer and longer and longer. So early in the universe, we saw a whole lot more mergers. We saw a whole lot more active galaxies. But as the universe has expanded, there have been greater distances with the voids, and the things that are going to merge have often already merged. And so it's a matter of if you live in a small town, you're not going to randomly walk into a neighbor as often as you will if you're in Manhattan. So over time, as our universe expands, as our galaxy falls into our nearby supercluster, as we become part of that Virgo supercluster, we're going to watch more and more galaxies merge into that central CD. And the rate at which collisions occur will get slower and slower and slower.
In fact, I mean, all of the good stuff has already happened.
Yeah,
I mean, we're already
largely
billions and billions of years after the really exciting times in the universe. Maybe 2-3 billion years after the Big Bang was when things were really happening. The stars were forming, galaxies were colliding. It was a mess. And now things are actually pretty settled down now.
Yeah, and eventually we will end up with so little gas and dust around that collisions are just going to be plain boring. It's just mergers of stars into larger systems of stars.
Yeah.
So gas and dust is a limited resource.
So hold on to it while you can.
Yes.
All right. Well, thanks, Pamela. Have a great time at the conference, and maybe we'll hear an update from you next week.
That sounds great, Fraser.
All right.
And
it's easy for you to save. Just press stop.
Yep.
But now you have to get it off the device.
Yeah, that part's easy, though. That part I don't worry about. Okay.
My desktop.
So I saw lots of scrolling on the. So I have my camera's up here, my computer's down here. So angular momentum makes the universe go round. Yes, it does. Maybe we should do an episode on the physics of pizza. No, that would just make me hungry.
Oh. Or pancakes.
Yes, I love pancakes.
So, as people know, I can make you a batch right now. And encourage NASA to be able to explore any part of space right now. Okay. Export my audio. I'm going to pause my Dropbox so that I don't kill my stream. And then pause. Okay. Oh, Dropbox. Okay, let's quickly sort of throw out some questions and then we'll go from there. William Van de Beek asks, do the dwarf galaxies that are currently cannibalized by the Milky Way have central black holes?
Dwarf galaxies actually don't seem to have them. This is one of those great confusions of all galaxies except the smallest seem to. Yeah, dwarf galaxies are just weird. Yeah, that's all I've got.
Okay, but I mean, some maybe. They're one of the places people are looking for intermediate black holes.
They are. So I studied the Ursa Minor dwarf galaxy as my master's thesis. It's about 65 kiloparsecs away, and you can make out individual RLRE stars and other stars in it. That's why I was studying it. What's kind of crazy is you look at it in radio and you see it has almost no gas and dust. Look at it in stars, and it's just this diffuse cloud. And if it does have an intermediate black hole, it's just hanging out naked. So we may not be able to find it.
Steve Chisel says, hey, did you guys see my earlier announcement? I'm going to be meeting Neil deGrasse Tyson tonight. We'll say hi to Dr. Tyson from us. Let's see. Matt Wood says he uses the Borg as describing galactic cannibalism. You'll be assimilated. Resistance is futile.
Yes, it's true.
Seb Dustmoney asks, so after the collision, will all the formation create supernovas over time and give rise to new nebula areas for a time with more heavy material? Does that question make sense?
Yeah. So when all of the stars go supernova, they will give off some material, but one of the things that we don't talk about as much as we should is those beautiful supernova nebula that you see are because the supernova is blasting out a bubble inside of existing gas and dust. So while there is material that's exploding off into the material that it largely gave off through its own stellar winds, a lot of that nebulosity that you're seeing when you're looking at like the Crab Nebula is material that was already there, that didn't have to do with the parent star, that just got pushed and shocked and made luminous. So some supernova will be more boring than others.
Sylvan Westby asks, how big are the biggest connected structures that will eventually emerge? Is it a function of total mass contained or just of the Hubble constant? Well, that's a really interesting question.
Yeah,
so
I'm not sure because I don't know how big the biggest superclusters are. So
yeah,
I
mean, people talk about this idea of this Laniakea supercluster and the Virgo supercluster, which is part of Laniakea, but there are portions of the Laniakea supercluster that are not really gravitationally bound, that they are expanding in a way that they will never come together. So is it appropriate to say that they are part of a cluster when really in the far future they're going to be, you know, dark energied away from each other?
Well, and this is where we end up changing what we call things. Like, we used to think that the Large and Small Magellanic Clouds were eventually going to merge to be part of the Milky Way, and we now know that they actually have enough kinetic energy that they're just going to fly away. They're going to leave behind stars and gas that we strip off of them, but for the most part, they're going to escape. So now they're just drive-by galaxy harassment rather than galactic cannibalism.
Right. A lot of people in the chat are talking about software that they like, and people are talking about Universe Sandbox and Universe Sandbox 2, and I couldn't agree more. Yeah, they're great. I met the developer at PAX this year and installed Universe Sandbox 2, and it's so cool. We've, you know, smashed all kinds of things into all kinds of, really, that's what you do, right? You take Earth, throw it into the sun, throw a lot of Earths into the sun, you know, smash the moon into the Earth, but you can do some more interesting, you know, reasonable stuff as well. They're really fun pieces of software. And of course, as well, people really like Kerbal Space Program. So if you're looking for some software to help you sort of understand orbits, gravity, things like that, definitely check out Universe Sandbox. And if you just want to learn more about rockets, check out Kerbal Space Program.
Yeah.
Okay, well, I think you've got to go find out what's going on with Pluto. So thanks as always. I hope you have a great time there in Houston, and maybe we'll see you Friday, and if not, we'll see you next week.
Sounds good. I think I'm on a plane Friday, but I'm not sure. So
okay. Well, hurry home.
I will.
But say hi to everybody.
Okay.
Yeah, and Steve, don't forget to say hi to Dr. Tyson for us all. We really appreciate that from all of Astronomy Cast. All right. Thanks, everyone. We'll see you guys later.